Now we look at three cases. Okay, one case, system is sitting here, positive directions, let's say this way, and we deliver an impulse. Okay, and of course we're going to let this thing keep oscillating. So we start at position, equilibrium position, which is going to be our zero position. We deliver a positive impulse, and if there's no drag, this thing keeps going. If there is drag, of course there's a drag term in the equation, and we're going to be able to deal with that. That's not going to be a big problem. Another possibility is we start over here at a positive position and let the thing oscillate. We release it at time t equals 0, so there it is, and it oscillates, and then at some point we come along and give this thing an impulse which causes it to oscillate more. Another possibility, we start it back here, we let it oscillate a little bit, and then we deliver an impulse at the wrong time right here, and we pretty much slow the thing down or stop it. Or maybe we let it oscillate and get back to here, and when it gets back to its extreme positive position, well, I didn't do that right, did I? Okay, apparently I've lost whatever coordination I used to have. Okay, so there, 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 there. Okay, so now we again accentuate the oscillation. So pretty easy to deal with these things using Fourier transforms, but let's make sure we understand how the graphs behave. Okay, if we start the thing at equilibrium and apply the impulse so that it begins oscillating, and it oscillates in the positive direction. Its initial displacement is going to be in the positive direction, or initial velocity. We're going to have then a situation where the position graph is a sine curve. Okay? Now we could have started it in the negative direction, and then we'd have the reflection of this curve. Okay? That would be like the negative sine function. If we start it from the positive position and release it so it swings back originally, then we have the same curve but maybe shifted to the left a little bit, and of course that would be a cosine. Now I'm just going to write down sine of t, but it could be like a sine of omega t, but we're familiar with that. And this could be like a cosine of omega t, depending on your period, your frequency, whatever. Okay, so we have that possibility. Then of course, maybe we bring it over to the negative side and hold it stationary, but then hit it with an impulse. Okay, and that would give us a graph maybe that looks like this. Okay, if on this sine curve we wait till we're here and deliver a strong positive impulse, that's going to speed the thing up. Now, of course, the speed is related, it's represented by how steep the graph is. Okay? If we apply the impulse right here where the graph has zero steepness, the graph is level, velocity is zero at this position, in other words, and apply an impulse, all of a sudden we're going to have a discontinuity in this function, and it's going to suddenly start upward like so, and having more velocity when it passes through the equilibrium position gives us more kinetic energy to overcome the potential energy increase as it moves away from equilibrium, if you remember the physics. And we're going to have something like this, and then we're going to then have a harmonic motion with a greater amplitude than originally. It's going to enhance the motion in that way. We could also apply that impulse at the top of the curve. Okay, if we apply it, let's say, don't want to do it here because I'll overlap but if we apply it here, then it's going to suddenly take off like this, and then it's going to start oscillating again with a greater amplitude. If we apply a positive impulse, and let's say we have this situation where we've released it and we allow it to swing back and forth. And if we apply that impulse at this instant when it's at equilibrium and swinging back this way, so that we have a negative velocity corresponding to the negative slope, negative velocity in this direction, and now an impulse, we could overcome the kinetic energy here and even push it backwards a little bit, or maybe we apply a little less impulse and it continues going forward but with less velocity. So we could, for example, at this stage, hit the thing with an impulse here, and then what might happen is we end up with a very small oscillation. You saw that. Or alternatively, a little more impulse, we could actually change the direction of motion and get a motion with a smaller amplitude that actually reverses the motion in this direction. Reverses it, but doesn't, results in a motion in the opposite direction. A motion at a lesser speed, but in the opposite direction. Okay. Then maybe, I believe in class and in one of the other videos, we actually did one where the behavior was like this, where we released the thing from here and so forth. And then we might have enhanced the motion in one way or another with an impulse, maybe at this point, and maybe a negative impulse at this point, so that it goes down like this and ends up with a greater amplitude. Okay, all those things are possible, and if we set up our equations properly, we can get solutions to these various situations.